and with me Dr. Ziad Abu Rob, also from the German Jordanian University, and both we will be chairing this chemical engineering kinetic sessions. It's our pleasure to welcome you here, and also I would like to welcome our speakers who are joining us online. Our first speaker would be Dr. Ibrahim Suleiman, and he will be talking about an equilibrium ab initio atomistic thermodynamic study of CH4 and CO2 adsorption on the alpha quartz 001 surface. Dr. Ibrahim is from Al-Balqa Applied University, and he has obtained his PhD in chemical engineering from the University of Newcastle, Australia in 2011. At the University of Newcastle, he joined the Priority Research Center for Energy Research under the supervision of Prof. Dlogo Groski in 2008, and he is currently an assistant professor at Al-Balqa Applied University. Dr. Ibrahim is keen to investigate in CO2 reforming system using density functional theory calculations. Welcome, Dr. Ibrahim, and the stage is yours.
Thank you for giving me this opportunity to talk about my study today. Today I will talk about an equilibrium ab initio atomistic thermodynamic study of CH4 and CO2 adsorption over the alpha quartz 001 surface. I am Ibrahim Suleiman from Al-Balqa Applied University. In this presentation, I will take you through a brief introduction about the applications and the importance of this study. Then I will give a brief description about the theory used behind this study. After that, I will highlight the main results and outcomes of this investigation. And finally, I will go through some conclusions and recommendations. Enhanced gas recovery technique utilizes CO2 gas in large scales, where CO2 gets injected in near drained wells to recover residual of hydrocarbons, notably methane. And in the meantime, CO2 gets sequestrated in the rocks of the well. And one of the major compositions in these rocks is alpha quartz, and therefore many studies have been carried out to study the adsorption and desorption of CH4 and CO2 over these materials. We are believing that CO2 and CH4 are competing with each other to occupy sites over the alpha quartz surface, and therefore the aim of this study is to investigate the stability of CO2 over alpha quartz and CH4 over alpha quartz structures and compare between these stabilities. The theory behind this investigation is well known as ab initio atomistic thermodynamics, and the aim of this technique is to bridge the gap between density functional theory calculations, which is carried out at 0 Kelvin temperature and 0 atmospheric pressure, to the real temperature and pressure of the systems. Equation 1 here describes the surface free energy gamma as a function of chemical potential mu of the species I with per surface area. The term EB here is nothing but the binding energy, and N is the number of species over the surface. Of course, equation 1 comes after a series of assumptions aimed to approximate the Gibbs free energy to the total energy of the system, which can be obtained directly from density functional theory calculations, and to bridge, to use the temperature or to include the temperature and pressure into the phase diagram or the surface energy phase diagram. We use equation number 2 here, and we can see that we have the first term, mu of T and P naught, is the chemical potential at any temperature and the standard pressure, and this term can be calculated using thermodynamic tables. The symbol K here is the Boltzmann constant, and B is the total pressure. Once we apply these equations, we produce a phase diagram in this figure. In this figure, the horizontal line here represents a clean quartz surface, and each of these lines here represent a system where CH4 is adsorbed on the surface. Each of these structures is characterized by two major things. The first is the adsorption site, and for this particular surface, we have four distinct adsorption sites. We're given the notations A1, A2, B1, and B2. And the second thing is the coverage over the surface. For example, the first structure, we have 1/4 monolayer A1, which means that the coverage or the number of species over the surface have the coverage 1/4 monolayer, and all molecules occupy the site A1. So if we look at this phase diagram, we can see that for chemical potential value less than minus 0.15 electron volt, the clean surface represents the most stable structure, which means methane, because this phase diagram is for methane. Methane prefers to be in the gas phase rather than getting adsorbed on the surface. But once we exceed this value, the system produces a more stable structure than the clean surface, and this structure is one monolayer A1 configuration. So we can see beyond the value minus 0.15 electron volt, we can produce a stable structure where CH4 is adsorbed on the surface and for the whole range of chemical potential. Similarly for CO2 over alpha quartz, we can see that for values of chemical potential of CO less than minus 0.22 electron volt, the clean surface is the most stable structure. But once we exceed this value, we start producing a more stable structure than the clean surface, and this structure has the coverage half monolayer and occupying the site A1. This structure remains the most stable until we exceed the chemical potential value here, minus 0.16 electron volt, where another more stable structure produced at 3/4 monolayer, and this structure remains the most stable until we reach the value of chemical potential minus 0.12 electron volt. After that, the coverage one monolayer with the adsorption site P1 becomes the most stable configuration or has the highest stability and for the whole range of chemical potential. Of course, when we are talking about the chemical potential of species, this means that we are increasing the concentration of those species in the environment, and we are reflecting this concentration because we are dealing with gaseous phase material. We are reflecting these concentrations in terms of pressure. So we can predict which of these structures can be observed experimentally at some sort of temperature and pressure by looking at this phase diagram. But to give this study a meaningful representation, a meaningful issue, we need to compare the phase diagrams of CO2 and CH4 because both molecules coexist at the same time in the wells. Therefore, if we look at those diagrams, we can see that CO2 over alpha quartz produces a more stable structure at lower values of chemical potential, which means if we have two species, CO2 and CH4, coexist together, CO2 tends to adsorb on the surface before CH4 and produce a more stable structure. And interestingly, if we look at the first stable structure for CO2 and the most stable structure for CH4 systems, we can see that both of them actually CH4 here occupy site A1 and there also CO2 occupies the site A1, which means CO2, when it comes on the surface, they start occupying the site A1 and prevent CH4 from being absorbed on that surface. Then, after the pressure or the concentration of CO2 increases, we produce another more stable site at 3/4 monolayer, and at this time, we have the site occupied by CO2 is the site B1. But again, because we have the surface now is crowded by CO2, we are anticipating that this will make a repulsion forces between the molecules, and again, CO2 will prevent CH4 from getting absorbed on the surface. So, in conclusion, among all CH4 alpha quartz configuration, we have only one stable structure that can be observed over that surface, and this structure is one monolayer A1. For CO2 over alpha quartz, we have 3 different stable structures. At lower pressure values, we have half monolayer A1 configuration, and at higher pressure values, we have one monolayer at site B1 system. The last point is actually kind of a recommendation rather than conclusion. This study was carried out with over alpha quartz with this system built using the silicon quartz lattice. So the unit cell for alpha quartz used in this study is based on a silicon quartz unit cell, but at high pressure, the lattice will transform to germanium quartz structure. So to give a more detailed description about how CO2 and CH4 can interact with alpha quartz surfaces, we suggest that we do both. We do the adsorption calculations using both lattices. The silicon quartz lattice will describe the low pressure regime, and the germanium quartz region will describe the higher pressure regime. So this will give a better picture for the CO2 and CH4 absorption on this system and how they can compete with each other, particularly the porosity of germanium quartz and silicon quartz are different from each other. Thanks for your attention, and if there's any question, yes, please.
Thank you, Dr. Ibrahim, for your interesting talk, and we have a room for just one quick question. Any questions?
Yes. We inject CO2 in near-drained oil wells and gas wells. So CO2 will push the residual hydrocarbons out of the well, and we can use most of the oil and gas remain in the well. Thank you.
Thank you, Dr. Ibrahim.
Dr. Ibrahim. Now our next presenter is Dr. Ma'moon Rawashdi. His talk is about preliminary evaluation of piston reactor technology for methane reforming reactions. He's from Texas A&M University at Qatar. Dr. Ma'moon is a chemical engineering assistant professor at Texas A&M University at Qatar since 2019. His research aims to develop energy-efficient, simple, and safe chemical processes enabled by innovation at the reactor and catalyst scales. Main applications are related to gas and hydrocarbon conversion processes to make low CO2 emission fuels and chemicals. Dr. Ma'moon, you have 15 minutes and the floor is yours.
Thank you very much, and it's a great pleasure to be here with you. So I would like to introduce this new reactor technology for all of you. It is called piston reactor technology. And first I would like to acknowledge this PhD student who are doing this work, Aya Abustrafa and Mari Kataba, and I'm doing this work with a professor called Patrick Linka. So let me start by this. Some of you will look at this picture and wonder, where is this picture from? Is it in the 18th or 19th century? Actually, this picture is just 100 years ago. It's in New York. What you can see very interesting in this picture is there is horses, there is a tram, and there is a car. Can you imagine how the city looked like at that time? And when you have horses, cars, and trams, I don't think this was like a normal situation. What we call this is a moment in a transition, basically, when you go from a technology to a technology, okay? This is the situation we are here today, okay? We have cars, well-established infrastructure. But the question is, are we ready to continue to the future? I don't think so, and none of us think so, yeah? We are changing slowly to many other ways. So basically, there are a lot of factors that influences the future. In 30, 40 years from now, probably the way we live will not be the same. Yes, we can see this in many places. Now, when you speak about process innovation, because we need to do a process innovation, it's not an option, it's a must, yeah? If we need to continue to live in a good way, then we need to innovate. Now, there are multiple ways you can innovate, either materials on the process or the equipment. My talk is about the process innovation at the equipment scale. Now, we all know that renewable electricity is becoming more and more available, and the prices of it is getting cheaper and cheaper. So this is the first premises. Second, we know that the cars and the engine technology is actually challenged by electric cars. You can see this very clearly here in Jordan with the introduction of electric cars. So what will happen later on? All the cars with engine will just get as a waste? We don't know. Another, basically, I'm coming from Qatar. So Qatar, for some of you who don't know, has one of the biggest natural gas reserves in the world, yes? So Qatar would like also to diversify and create sustainable processes related to methane conversion. So what is the project idea? The project idea is we bring an engine, which is a commercial technology, but we will repurpose it and use it as a chemical reactor for the production of chemical. So in this example, the exhaust from the engine is not a waste, it is the product, okay? So it's a completely reinventing a technology we know very well, but in introducing it in a completely different way. Now, some of you will wonder, is this a new idea? Not at all. This has already been explored even from the beginning of car industry. 100 years ago, people were trying to make nitric acid using this technology, okay? Now, when we started this project, we went and did the kind of review just to know what has been done in this field. Now, what was the most interesting thing is you can see there is only less than 100 articles and patents related to this technology. What is very interesting about it is that the majority of work is patent, and it's not even a literature, which shows that actually the guys who got the idea of this project is the guys from the industry, because they know what it means to use this idea. Where it has been used so far, a lot related to methane chemistry, to chemicals, and also nanoparticle synthesis, and basically destruction of materials. So let me explain you the analogy of this technology. This is just a car engine that goes through a 4-stroke engine cycle. So basically, what happened is, sorry, this is going very fast. Every fraction of a second, the pressure inside the piston increases to tremendous high pressure. You can even reach easily 300, 400 bar. Now, because of this rapid compression, the temperature increases also a lot. So what it means, I'm operating at temperature pressures never operated before for a fraction of a second, although my equipment is at normal condition. This is exactly how a car runs. So, for example, if I have a chemistry in which the intermediate species is the desired one, we can maximize that intermediate because I have rapid heating and rapid cooling, okay? Now, if you will compare the operating window of this reactor technology to other existing reactor technology, you can see that the majority of reactor technology we have today is at kind of intermediate temperature and pressure. You either have very high temperature or also very high pressure. So this definitely means we have a new operating window to carry out chemistry for the first time, never done before. So you can even have a lot of other advantage like size, like you can even kind of combine multiple pistons in the same way to get even work and heat. So basically you can have more option for energy integrations. And this technology is well established. It just need to be repurposed to be used as a new way. Now you can ask yourself, you can ask me, since its invention 100 years ago, why we cannot see any of these technologies to date commercial. And it has been tested for many different applications. One of the reasons is a lot of technological challenges, like limitation of the lubrication, sealing, leakage, throughput, wearing, because the equipment is not designed as a chemical reactor, but rather as an engine to get heat and work. Another reason is actually even the main reason is when you work with technology to innovate new technology, if you try to do what we call incremental innovation, the market and the methodology to innovation is very clear. But when you want to do disruptive technology, then basically you don't have a reference to compare to. You don't know where are you going. It's basically everything is open. So basically, how can you analyze and look for a technology that doesn't even exist today and analyze it in a good way? And this is basically the approach we propose in this project, which we build the entire project on that. So the first is we take the process design and synthesis right from the start, even before it is even validated. Why is that? Because simply I can know the gross margin, I can know things about economy of scale and things related to, for example, heat options, because this will allow me to know if this technology even makes sense to start with or not. Second is we build a model to allow us to extrapolate, kind of judging. Of course, maybe this is not correct, but at least you have a ground to build up and explore this technology. At the same time, we build an experimental facility to screen different chemistry and find out the right chemistry to basically build and use this technology. These three tools together, we combine to assess a technology that hopefully in the future can make an impact. So the first tool is the process design and synthesis. What means synthesis is we synthesize processes that doesn't exist, not molecules, but processes. So if I will take methane reforming, which is a very well-established and mature technology, these are the two ways of producing hydrogen from methane. You either go via steam methane reforming or partial oxidation. So what we did, we took data from the literature for the piston reactor, and based on the data from the literature, we constructed a flow sheet. And then we tried to compare the processes. Now, this is a big table. You don't need to look at it completely. It basically compares these three routes for different metrics. One of the first things that I want to show you, for example, if I will look to the CO2 emission, it is shifted this. I don't know why. It's just because of PowerPoint. So basically, we have here CO2 emitted in a normal technology is around 8.2, while in the piston reactor is 12. If I will look to the cost, hydrogen produced in the piston reactor is 3 times more compared to the technology. So some of you will say, this is already a bad choice. However, we know because the process is different. Actually, if you look here to both the processes, the partial oxidation of methane uses air, uses oxygen, while in the piston reactor they uses air. So the introduction of nitrogen increases the entire capacity of the plant, and basically the separation technology completely changed. So the entire cost of the production changes. Now, I can keep just working on cost, but in reality, to develop a new process for the future, you need to account for other factors. So here we introduce, for example, what happened to the CO2 emission, because this is a critical and a major issue to go forward to the future. So we start thinking about where to put the CO2 and stuff like that. No need to look in details here. So the message is, just using the process right away in the start targeted us where should we focus to develop this technology. So we know we should avoid using nitrogen, because nitrogen is just basically increasing the cost of the plant. We need to operate this reactor at much higher pressure, because this is the requirement for the process. We need to increase the single pass conversion. And also, most important, we need to maximize the amount of heat. The amount of heat will help us to capture the CO2 for free. So basically, combining this knowledge, we only can capture because we did the process in the beginning and not later on. Another thing we did is we developed a reactor model. So simply this describes how a reactor basically performs, is you get a temperature and pressure increase and how the chemistry changes along the way. This is what you would like to understand when you carry out such a chemistry in this reaction. So what we did is we took simply a zero thermodynamic model. We took kinetic from the literature, although they are not developed for this technology, but we just took it there and we assume it is correct. And then we did a kind of iteration in MATLAB and basically develop a kind of a reactor model. We are not sure if it's correct or not, but at least we use a model to help us think about the process, position it, how it works. So we validated our model with some literature data, and we know that if the temperature profile, we managed to get it correct, everything in the chemistry matches. So this was a key that allows us to understand how the model behaves and how to use this one in the future. So what did we do with the model? It helped us to do a complete full and mass energy balances. Some of you will think, but this is a trivial. But if you work with a new technology, you don't have that information. So if you want to do assessment, you need the full information of energy and mass balances. Again, we use these models to do parametric study to understand what happened if you change temperature, if you change speed, and then what happened to the hydrogen production, what happened to the CO2 emission, what happened to the quality of hydrogen we produce. We also saw and analyzed how much work and heat can be produced using this technology, because this technology is unique. It produces also work and heat, not only just product as a chemical. So after that, we did a kind of a scale-up study. So if you go from small scale to larger scale, how does it look like? So we did a lot of analysis. We don't need to go a lot in details. I just want to highlight a couple of things. If I will compare how much hydrogen produced compared to the reactor volume, it was more than 20 times smaller reactor to produce the same capacity. This is a massive improvement in the process. We are not doing small changes here. So with this model and this tool, we managed to make full information on the energy mass balance essential for the evaluation. We managed to make a parametric study to identify basically how to optimize and think of the process, the limitation and opportunities, and also, although this methodology might not be true, but if it is valid, it means we can really screen a lot of chemistry quicker to help develop this technology further. The last thing, which is, and I'm finishing it quickly, we developed a testing station. So how does it look like? We have an electric motor, a torque meter, a piston reactor, which is simply an engine we just bought and connect, and we have an in-pressure cylinder, mass flow meter, and furnace. So basically, the setup is still under construction. We will try to do different chemistry, and we will analyze the in-cylinder pressure, because that's the only information you obtain what happened inside the piston. Yes, you cannot measure this with temperature. It's extremely too fast, the measurement. And the product we will analyze using GCMS. This is just a picture showing how the pressure profile change inside, and this allows us to understand how to operate the process, and if our analogy of working with this setup, it makes sense. This is my last slide. I think this technology holds a lot of promises in the future, but still a lot way to go. And we think the holistic approach we chose by developing multiple tools at the same time from the start will help accelerate this process. This work is funded by the Qatar National Research Fund and by Shell as the industry partner who funded this project. And basically, I also would like to announce that I'm looking for a PhD student related to catalyst testing. So if any of you is interested for a PhD position, please feel free to contact me or talk to me after this talk. And with this, I would like to thank you all for listening to my talk. Thank you.
We have room for one question. إذا تكرم الدكتور على المنصة.
Well, thank you very much for the nice presentation. I was just wondering about the scale-up data that you mentioned there. Was it just out of simulation? This hasn't been tested on a larger scale, or?
So we have done.
How did you do it, or how did you get the results that you?
It's not here. So we have data from the literature, experimental data. We validated our model to that. So on the small scale, we have experimental data on the small scale. And then we simulate what happened if you increase the piston size. Now, our model considers the whole cylinder as one zone. So it doesn't take into account back mixing. But we know, of course, this is probably not work well. But what surprised us, it doesn't, in this technology, it doesn't mean that bigger cylinder mean better scale up. If you have a small but very high RPM, sometimes you get even more benefit. So this is even to our surprise. Sometimes you think increasing size will always mean bigger capacity.
And this is just based on the simulation. Nothing real was done.
Now,
right?
purely, one case was validated, the other cases are extrapolation.
And the validated case was on the small scale, not
On
the
small
large
scale.
scale.
Small scale with 400 cc.
So nothing in the literature on a process
In the
that
literature,
uses this
there is
approach.
89 articles only. 40 of them is patent, 44 is patent, and 40 is article. This is something you don't see often, that basically. So simply, there is no experimental data.
It looks very interesting, and I'm just wondering, like, why in the research nobody has done it before?
Yeah. Thank you.
شكرا يعطيك العافية دكتور.
Okay. Thank you very much.
Thank you, Dr. Mamoun. Our next speaker is going to be Dr. Messia Bahia from Algeria, who is joining us online via Zoom. And he will be, or he or she, I don't know actually, will be talking about synthesis and characterization of a fluoroperoxide KZ and F3 compounds. Dr. Bahia, are you with us?
Yeah.
Okay, can you?
I'm here.
Okay, thank you. Can you please turn on your camera? And the screen is yours. You can start.
Okay. So, could you see my screen?
Yes, yes.
Okay. So, hello everyone. Welcome to our presentation in the Shanda International Chemical Engineering Conference. So, our presentation targets by synthesis and characterization of fluoroperoxide, KZN F3 compound, prepared by Mr. Bahi and Rashid Makhloufi. Abstract. This study was largely part of research access whose objective was the synthesized structural and physical characterization and development of materials from fluoroperoxide, KZNF3, which is solid solution bioliquid, soft chemistry. The synthesized phase were characterized by XRD, FTIR, and particle size analysis, which is kind of elementary characterization. There is a lot of other characterization parts which needed to be done. So, the complete description of the X-ray diffraction pattern was made by the rate volt technique, including background, shape, position, and intensities of the diffraction patterns, which is simulation of the X-ray diffraction after the synthesis of this powder. So, including, observed using the structural model using of the C file, the parameters of the model have been refined by lattice squared technique to obtain a good match as possible between the observed and calculated diffractor bands. So, we'll start with the preparation of the material. The co-precipitation makes it possible to obtain precursor products by simultaneous precipitation of two cations, which is M and M+, M being the alkali and M+, which the alkaline earth metal or transition metal. This method consists of using solution of KF during the co-precipitation, as mainly KZ and F3 are formed as there are a limiting reagent in solution, which is K+, the ion of potassium, and the ion of the zinc, which is Zn2+. So the excess reagent will remain in the form of the ion solution. So there are several liquid synthesis processes. We present the precipitation process that we'll want to use to synthesize the metal studies in this work. This work will present the experimental protocol of the synthesis of fluoroperovskite phase and, by co-precipitation, taking advantage of the complexation of the F fluoride ions in solution. This method using to prepare this powder for reason of time availability of X-ray diffraction, because the main reason of this precipitation is the characterization and to prove the presence of KZ and F3 and to simulate the X-ray diffractions or patterns of those powder by using simulations softwares. So approximately 15 grain of sodium fluoride and 13.63 grain of zinc chloride are dissolved in aqueous solution. The solution is heated to 80 degrees Celsius with stirring. The solution is cooled and filtered through Bachmann foam. The product obtained is dried in oven at 120 Celsius degree. So we will start with the results. The X-ray crystallographic analysis of powder is a very convenient method to know the various phases of the mixture, the proportion, the crystalline structure, and to determine their domain of existence. The X-ray diffraction of this study is made by using Barker D8 diffractometer installed in the University of Muhammad Liari research lab. So we could see in figure number 1 the power diffractogram of the KZ and F3 composition prepared by the co-precipitation. So the results obtained clearly confirmed the formation of KZ and F3 phase by the co-precipitation method. The powder obtained is well crystallized and identical to that indexed. The complete description of the X-ray diffraction pattern was made by the rate vault technique, including the background, shape, position, and intensities of the diffraction patterns, observed using the structural model using the C file. The parameters of the model have been modified by latest squares technique to obtain as good a match as possible between the observed and the calculated diffractogram. As we could see in figure number 2, the part A is the powder synthesized diffractogram of the KZNF3 composition prepared by the co-precipitation. Part number B is the real Venn diagram resulting from the reference of the structure of the compound KZNF3, and number C is the presentation of the structure of KZNF. So figure number 2 from A to C presents the reference patterns of the synthesized KZNF3 nano powder. So initially, the reference products were carried out following the adoption of the various needed information of the structure of the KZNF3 is described in cubic form, which is clearly shown in the part C of the figure 2, where the contour of the face are occupied on the centers of the faces are occupied by the atom of F, and the summit of the cube is occupied by Q, which is potassium atom, and the centers of mesh occupied by the atom of Zn, which is the heavy metal. Sorry. Sorry, I have, so table number 1 shows the radiocrystallographic characteristics of the accuracy conditions of the structural reference parameters of the new KZ and F3, which give us the information about the parameters, the angles, the volume of the cube, and the space group, and the atomic positions. Finally, we have the FTIR spectrum. Sorry. We have the FTIR spectrum, which is shown in figure number 3. The FTIR is based on the absorption of the infrared radiation by the material analysis in inorganic solids. The study of infrared absorption phenomenon makes it possible to identify certain groups. In our case, the vibration band of the KZ and F3 structure provides structural information from their vibrational properties. The FTIR transfer spectroscopy study was carried out on the powder. We will, as shown in figure number 3, we could see the vibration related to the band of the Z and F at 440. So the last one is the particle size. So the figure number 4 summarizes the results of the particle size analysis of the KZ and F3 composition. So the concerns are the KZ and F3 powder prepared by co-precipitation. The size description of the grains is almost homogeneous, around 1.5 micrometer. The description around 15 micrometer can be attributed to an agglomeration of the grains. So, conclusion. This study was largely part of the research accessible objective is to develop the material from the fluoroperovskite KZ and F3 family, which is a solid solution by liquid, soft chemistry. Zinc chloride is an alkaline earth mineral, is where particularly of the same charge of the very similar ionic residues, which made it possible to form the KZ and F3 phase. The solid solution, which was synthesized by the soft chemistry method, known as co-precipitation, the formation of the perovskite phase, was used the complexing powder of the fluoride ions in solution with the metal president and results in the pure KZ and F3 phase. The synthesized phases were characterized by XOR, the perovskite phase of KZ and F3 characterized in the system and adopts the same crystal structure, favors the co-precipitation method. Furthermore, the crystallite size value obtained from the rateful refinements showed the opposite trend of the WH value. The modified tolerance factor value 3 were extremely close to the unity, indicates a strong perovskite structure. The results of infrared confirm the formation of KZ and F3 for previous gate phase. In fact, the zinc atom being hidden, and consequently the characteristic band of vibration Z and F shifts toward the low value of wave number, frequency, vibration, and energy. Thank you.
Thank you, Dr. Bahia, for your valuable talk. And we have time for one question, please. One quick question. Any questions? No questions? Okay, thank you, Dr. Ziad.
Okay. Our next presenter is Dr. Muhammad Liari. His talk is about pyrolysis of high-density polyethylene kinetic study. The affiliation of Dr. Liari is Chemical Engineering Department at King Faisal University in Saudi Arabia. Dr. Muhammad is the chairman of the Chemical Engineering Department at King Faisal University in Saudi Arabia. He got his PhD degree in Chemical Engineering from King Fahd University of Petroleum and Minerals in 2013. His research interest includes plastic waste management, flow assurance, and emulsion technology. Dr. Liari, you have 15 minutes, and I hope you are hearing us or you are online. Dr. Liari?
Yes. Can you hear me?
Yes, sure. You have 15 minutes, and the floor is yours.
Yeah, thank you, Dr. I think this is Dr. Ziad, isn't it?
Yes. Ziad is with you.
Yeah. So, assalamu alaikum wa rahmatullah. Greetings, everyone. Thank you for the nice introduction. It was my hope really to be attending this kind of event in person, but unfortunately I could not because of some of commitments here in Saudi Arabia nowadays. So, in this presentation, I don't know whether can you see my slides?
Yes, we can.
Can you see my slides?
Yes, we can see them.
Yes. Just a minute. So in this, so today I'm going to present base of my recent work, which is titled as the pyrolysis of high-density polyethylene. So part one is the kinetic study. So in this presentation, I'm going to talk briefly about the problem itself, and then the research scope, experiments, results, and I end up with some conclusions. So as you know that the environment is suffering a lot from the massive amount of plastic that we are unfortunately generating day by day. And as you know that the amount of the generated plastic waste has increased by more than 20 times within only 70 years. And now as you know that the rate of the generation of the municipal solid waste has reached 2 billion ton per year, and it's expected to increase by 30% by 2030. In Saudi Arabia, 5.28% of the municipal solid waste is plastic waste. And unfortunately, in 2014, the generation rate is 15.3 million ton per year, and it's expected to be doubled by 2033. In addition, also, the annual production rate is still much higher than the recycled one. And unfortunately, most of the plastic waste is either incinerated or disposed in landfills, which is against saving our environment. The recycling process for sure has some limitations due to the availability of some additives, and the pyrolysis of plastic waste is one of the promising alternatives because of their valuable products as well also their friendliness to the environment.
The monocycle plastic waste contains mainly low-density polyethylene, high-density polyethylene, polypropylene, polystyrene, and polyethylene terephthalate. And in this work, we tried really to obtain the kinetic parameters, the activation energy, pre-exponential factor or frequency factor, and the reaction mechanism of the pyrolysis of high-density polyethylene at 4 different heating rates. And also we tried really to define a step-by-step procedure to obtain the kinetic parameters from the experimental data. Initially, we did characterize the samples of the high-density polyethylene powders by doing some sort of the analysis using proximate and ultimate analysis. And if you could see here, the volatile content is very, very high, and the carbon content and hydrogen content is very high. And this means the pyrolysis of high-density polyethylene is promising. And the nitrogen content and ash and sulfur is almost either zero or negligible. And this is also can give us an indication that the pyrolysis of high-density polyethylene also cannot harm our environment like the disposal of the plastics to the environment. So we did really do some sort of TGA analysis, thermographic analysis, using pure nitrogen flowing at 100 milliliter per minute at 4 different heating rates, as I told you. If we define the reaction rate of the pyrolysis of high-density polyethylene by this equation 3 for non-isothermal pyrolysis, or we can represent this equation by equation 4 in the integral form. The integration, the temperature integration here cannot be solved analytically, and approximation has to be made to get the solution of the integration form. And that's why different researchers really did end up with some models. And in this investigation, I did selected 3 of the most used isoconversion models, and one of them is for the non-isoconversion models. For the isoconversion models, FWO, CAS, and STARMEC, I use them really to obtain the activation energy from the experimental data, and then I used Coates-Ridderfen to determine the reaction mechanism. After that, I went back to the isoconversion model to obtain the frequency factor from the slope of each equation, as we can see here. Starting with the thermographic analysis, this is the TGA or TG camps, we call it thermographic camps. As you can see here, as the heating rate increases, the onset temperature, the peak temperature, as well as the end-set temperatures will shift to the right, means to the higher temperatures, or we can say that the weight loss is reduced by increasing the heating rate. And this is the derivative thermographic curves, as you can see here. So it's clear that the temperature of the peak has been shifted to higher temperatures, and the size of the peak also has increased, and this is due to the fast heating rate or fast rate of the heating. For the activating energy, what we did after obtaining or collecting the TGA data, we used the models presented earlier to obtain the activated energy at different conversion. So as you can see here, A is for the using the MWO, B is for the CAS, and C is for the STARMEC model, and these are the results. So if you could see the results, all the models give us almost the same value of activation energy, and this is good. That the experimental data were okay, and the analysis also were okay as well. and the regression coefficient is more than 99%, as you could see in this table. After obtaining the activation energy, we went back to use the Co2 model to obtain the activation energy for each reaction mechanism. So here we tested 15 reaction mechanism, well-known 15 reaction mechanism, to obtain the most suitable one. So by comparing with the value of the activation energy, as you could see in here, the reaction mechanism is third order reaction. So this is based on the analysis of, as you could see. After that, we went back to the algae conversion models to obtain the value of the frequency factor, but this is in lim form, as you could see in here. After that, really we have to check the suitability of the reaction mechanism by investigating the linear relationship between ln A and the activation energy, and we succeeded really to do so. As you can see in here, we had also straight line equations with the high regression coefficient, as you can see in here. In conclusion, in this investigation, step-by-step procedure to obtain the kinetic parameters, the activation energy, frequency factor, and the reaction mechanism has been outlined or clearly defined. And also the pyrolysis of high-density polyethylene has been investigated at 4 different heating rates. And we use 3 integral conversion methods to obtain the activation energy values at different conversions. And then the average value were compared with the obtained value by Co2 at different mechanisms to identify and determine the most suitable reaction mechanism, and we ended up with the conclusion that the reaction mechanism is third order. And the pre-exponential factor has been calculated after that, and the suitability of the reaction mechanism has been confirmed by having linear relationship between ln A and the activation energy. Thank you very much, and I'll be glad to answer your questions. Thank you.
Thank you, Dr. Liari. Now we have for like a couple of questions. Any question? Okay, no questions. Thank you very much for your interesting talk. And now we move to the next presentation. Thank you very much, Dr. Liari.
Okay, our next speaker from Greece via Zoom is Anna Mireille. And he will be talking about, or she will be talking about, ultrasound effect on 5-CQA and tryptophan reaction, assessment of the reaction kinetics and the product's physiochemical characteristics. Anna, are you with us?
Hello.
Okay, the screen is
Hello,
yours.
can you hear me?
Just you have 15
Okay,
minutes.
thank you.
Sorry, you have 15 minutes for this session, okay? Thank you.
Okay, can you see my screen?
No, not yet. السكرين تبعتها موجودة؟
How about now?
No, nothing on the screen.
Okay, because I can see from the Zoom meeting that you can see the screen. Maybe it's the internet or something.
No, make sure that you are sharing it from your side.
Yes, I am. I'll try this again.
Okay, 1 minute. Yes, okay.
Okay.
Sounds like we have some technical problem. Just give us 1 minute, please.
Okay. Have we connected? Shall I try again?
No, not working yet. We are working on it.
Okay.
What's the problem, Ziad? Try share it now from your side, Anna, please.
Okay.
Yes, no, wait. We can just see the logo of the conference.
Yes.
Okay, yes, it's working now.
Okay.
It's working now.
Okay.
Thank you. And sorry for this.
There's no problem. Hello, my name is Anna Maria Menelau, and I am a student at Aristotle University of Thessaloniki. And in cooperation with Dr. Valentis Patropoulos, we have studied the ultrasound effect on 5-CQA in tryptophan reaction. Experiments took place at the laboratory of food industry technology and agricultural industries. Chlorogenic acids are biologically important phenol compounds produced by plants and are mostly present in certain fruits, vegetables, and plant species. There are many advantageous health benefits linked to the chlorogenic acids family. The reaction between 5-CQA and amino acids commonly leads to greening of the mixtures. An exception to this was the formation of a red color in a reaction between 5-CQA and tryptophan. Ultrasonic treatment has become a popular method due to its multiple advantages, including reduced energy requirements, waste prevention, and improvement in mass transfer, which in turn can speed up a chemical reaction. The chemical and physical effects of ultrasound are caused by the cavitation phenomena that occur. When the bubbles form through cavitation collapse, they cause very high instantaneous temperatures and pressure. The aim of this research work was to speed up the reaction between 5-CQA and tryptophan by applying ultrasound and study its kinetics. Experiments were then conducted to investigate the effect of the temperature on the reaction. Furthermore, the product of the reaction was tested for its physicochemical properties, such as stability against heat treatment, antioxidative, and antimicrobial properties. Finally, its potential role as food colorant instead of nitrates was explored. The reaction mixture was placed in an ultrasonic bath at 40 Celsius, while samples were analyzed by UV spectroscopy and HPLC for 8.5 hours at regular intervals. The reaction was also performed at 63 and 73 Celsius. Different TRP concentrations were also tested in order to investigate the effect of TRP concentration on the kinetics. The product of the reaction was freeze-dried and a red powder was collected. The powder was redissolved in 10 ml ultra-pure water and subjected to extreme temperatures conditions to test its stability and different heat treatment. Specifically, the stability was tested using a water bath at 100 Celsius for 20 minutes, a freezer at minus 18 Celsius overnight, an ultrasound at 40 Celsius for 15 minutes, and a microwave at 700 watts for 2 minutes. Samples of pure 5-CQA and the product of the reaction at concentration of 5,000 ppm were tested for the antimicrobial activity against various bacteria. The methods agar well diffusion and minimum inhibitory concentration using microplate were used. 3 cooked pork sausages were prepared following the same recipe. Then sodium nitrate and the product of the reaction were added to separate mixtures and blended under cold conditions till all ingredients were evenly distributed. One mixture was then added in one sausage and the other was added in another sausage, leaving one sausage plain. Sausages were placed at a refrigerating temperature and daily measurements were taken to determine the oxidation level of each sausage during the 8-day refrigerated storage. Oxidation of myoglobin and color change in the sausages was followed by measuring the oxymyoglobin concentration in the sample spectrophotometric. The absorption of the filtrate at specific wavelengths was measured and the percentage content of myoglobin formed were calculated. The concentration of the reactant 5-CQA was followed by HPLC. Indicatively, in Figure 2, the chromatograms of the reactant mixtures at 0 minutes, 70 minutes, and 390 minutes are shown. The first peak was at first identified as TRP. At 70 minutes, the area of the first peak slightly decreases compared to 0 minutes, while at 390 minutes, the area has increased again. Consequently, it is assumed that the total area of that peak is the sum of the area of the red pigment's peak, where increases with time, and the area of TRP's peak, which decreases with time. The second peak was identified as the second reactant 5CQA. During the reaction, the 5CQA peak was decreasing and it was not detectable after 6.5 hours. In order to determine the order of the reaction, two hypotheses were formed. Specifically, the first hypothesis indicated that the reaction follows first-order kinetics, and the second hypothesis indicated that it follows second-order kinetics. If the first assumption was correct, then the data fall of the two axes shown in Figure 3a should have a linear dependence. Instead, a curve is formed, which concludes that this hypothesis cannot be confirmed. The second hypothesis seemed to be correct since, as shown in Figure 3b, there is a linear dependence. Thus, it is concluded that the reaction is a second order and the reaction rate constant was calculated. To further investigate the reaction order, experiments with various concentrations of the reactor were performed. By solving initial rate equation, it is concluded that the reaction is second order in A and zero order in B. Therefore, the global order of the reaction is second order. The rate constant was calculated for each time point, and the final result is obtained as the average of the individual constants. To verify that the reaction order is 2, initially the rate constants were calculated for the first order reaction. The table clearly shows that the first order kinetics cannot be applied in this case. Experiments have been chosen to take place for tryptophan concentration from 6 to 14 millimolar because, according to the literature, concentration lower than 6 millimolar produce a brown color. As shown in Figure 4, the most concentrated red color is observed when the concentration of 5CQA and TRP are 1 and 7 millimolar respectively. The highest color difference was observed for samples 4, where TRP had twice the initial concentration of samples 1 and 5, where 5CQA had half the concentration of the sample. It was observed that by increasing the temperature, the reaction time decreased significantly. At 40 Celsius, the reaction takes place in 8.5 hours, at 63 Celsius in 5.5 hours, and at 73 in just 3 hours. However, the color changed gradually from red to brown. This may be due to adverse reaction that may occur at higher temperature, or possibly due to the destruction of one or both of the reactants upon exposure to those temperatures. It is noted that the red pigment exhibits remarkable stability to different sources of heating at neutral pH conditions. Reaction product did not exhibit any significant antimicrobial action. Nevertheless, 5CQA on its own is a non-antimicrobial agent. However, when it reacts with tryptophan, there is a negligible amount of 5CQA remaining in the final product. In Figure 6, it is observed in all 3 samples that the oxymicrobial percentage value falls sharply on the second day of storage. The sample that did not contain additives shows the largest drop. It is also observed that on the remaining days of storage, the percentage of oxymicrobial in the samples with the additives decreased slowly and at a similar rate, maintaining to a large extent the original color. Another important parameter that should be compared was its antioxidant properties. Figure 7 depicts the formation of secondary oxidation products during refrigerated storage of the cookbox sausages as measured by T-bars. The sample without additives from the second day began to show a higher concentration of MDA than the other 2 sausages containing additives, while showing visual signs of oxidation at the same time. On days 3 through 8, the samples with the addition of reaction products exhibited significantly lower oxidation than the control sample. The spectrophotometric analysis of the samples was performed on the 2nd to the 5th day of the preparation and on the 22nd day of storage. In the sausage containing the product from the reaction, there is a decrease in absorption over time, while the color of the sausage fades slowly. On the 22nd day, it is observed observed that it still absorbs at a wavelength of 422 nanometers, and that its absorption decreased slightly compared to the fifth day. This was also verified visually in the sausage. As for the sausage that contains sodium nitrate, its absorption remains constant for the first 5 days, but on the 22nd day, there is a visual alteration acquiring a gray color. In conclusion, in this work, it is reported for the first time a significant decrease in the reaction time from 24 hours to 8.5 hours by means of ultrasonication. The global reaction order was estimated at 2, with 5 CQA order being equal to 2 and tryptophan to 0. The reaction constant was also calculated. The red pigment had no significant antimicrobial properties. However, it exhibited antioxidant properties similar to those of sodium nitrate as measured, and most importantly, showed remarkable heat stability. The latter property broadens the spectrum of its potential application in the food industry. Thank you for your attention.
Thank you, Mary. Any question? No questions. Okay, now we will have a 20-minute coffee break, and after that there will be a keynote speech to be delivered by Professor Abdulaziz Khlefat. Thank you very much for your presence here, and enjoy your coffee.
Related to the impact of Dead Sea and Dead Sea Canal. So, for those who are from outside Jordan, to shed some light on the uniqueness of the Dead Sea. The Dead Sea actually is the lowest point in Earth. It is unique by its level decline that goes at a rate of almost 1 meter per year. Although some oceans actually level is increasing due to global warming. When it comes to salinity, the Dead Sea is the most saline lake or closed lake, with almost 10 times as saline as the ocean. In addition to the level decline, salts accumulation at the seabed is at a range of 10 centimeters per year. The other thing, the main contributor to Dead Sea water body is Jordan River, where the inflow from Jordan River toward the Dead Sea used to be 1,300 million cubic meter per year. This was back in 1930s, while in the year 2000, actually this flow rate dropped to 300 million cubic meter per year. Well, Dead Sea nowadays is going through an ecological issue, which is related to the level decline. If you look at this figure, what can you notice? You can notice that up to almost 1970, the Dead Sea level was basically steady, which means the water balance of the Dead Sea was okay. But later on, due to human interaction and human involvement, let's say in certain areas, the Dead Sea level started to decline. And if this decline continues at the same pace, definitely one day Dead Sea might be lost. But of course, working against the nature does not always work properly. So in order to understand this better, we have to look at the water material balance. What goes into the Dead Sea actually is about 210 million cubic meter of water that comes from western and eastern springs, from direct rain that goes into the surface or into the Dead Sea through its surface, and some runoff. Now, what goes out by evaporation is about 700 million cubic meter, in addition to what's taken by industrial activities, 160 and 125 million cubic meter, which adds up to 985 million cubic meter. So, one can notice that there is a deficit of 675 million cubic meter per year. Where can we get this from? Eventually, this is a big issue. And the main cause for this is diverting the water that was allocated for the Dead Sea by nature and used by some, let's say, industrial activities, which is minimal. It goes to almost up to 15% is used by industrial activities, while the 85 decrease in almost 1,700 million cubic meter per year is caused by humans or by human acts. So this is one good example related to water harvesting projects in both sides, actually, of the Dead Sea and the Jordan River. Okay, these are the dams constructed in riparian countries. So if you look at the major dams, and I believe most of you know this and visited this, so it could capture up to 35 million cubic meter per year. So what was given by nature to flow toward the Dead Sea now is not the case. So there is another share that restricts basically the steadiness of the Dead Sea. Regardless what happens to the Dead Sea, we still love it to death, and wherever it goes, we're gonna follow it. We're gonna follow its shoreline. That's why people recently thought of ways to save the Dead Sea. There were many plans starting from the 70s and 60s of last years to bring water from the Mediterranean to different routes to the Dead Sea, but definitely they failed because their main objective was not to save the Dead Sea. Recently, and the most viable plan is to convey water from the Red Sea to the Dead Sea, from Aqaba to the Dead Sea, and this could be a viable choice. But the best choice actually is to address the cause of level decline, which is impossible to reach. In 2007, there was a call actually to study the impact of this project to deliver water from the Red Sea to the Dead Sea. And of course, this project entails many activities, and one of them is to utilize the mineral drop, or let's say water flow by gravity, creating very high pressure that can be used for hydropower and desalination or using reverse osmosis. And then the 1,140 million cubic meter per year of projected brine can be dumped into the Dead Sea to alleviate the level drop. This was one of the scenarios. The other scenario is to convey seawater directly to the Dead Sea. Well, in that call for a proposal to provide consultancy, one of the items was related to mixing Red Sea and Dead Sea water. As it was mentioned by Dr. Adnan, at that time I was working at Muhammad University, mainly in the Dead Sea Center. And we submitted a proposal for the sake of carrying out this component. And we reached out to Arab Potash Company for possible funding. And definitely Arab Potash Company did not turn us down. And then we started thinking about what will happen if we mix two water bodies that have different or completely different composition, as you can see in this table. So the Dead Sea composition in terms of iron exceeds the Red Sea almost in 10 and more fold. The only thing that is missing is sulfate, but definitely the Red Sea is rich with sulfate, and the Dead Sea is rich with calcium, and this might create some problem. So the projects entail many activities, starting from the first one which is monitoring. And monitoring here is, when we say monitoring, we have physical and chemical monitoring of the mixed water bodies. The next activity is to see whether there will be gypsum creation, and what will happen to the salinity of the brine, whether trace metals eventually get precipitated or not, and what will happen to the rate of evaporation, of course, due to mixing, and whether biological organisms will have a rich environment for them to be alive. So we decided to have our experimental site as close as possible to the Dead Sea, and the site was selected to be in the southern shore next to Arab Potash Company point of intake. It's about 100 meters actually south to the Dead Sea. And it was located at an elevation of -4 or 5 meters below sea level. Nowadays, the sea level is about 432 meters below sea level. So the experimental site consisted of 6 ponds, and those ponds basically are made of cylindrical, let's say, vessels or reservoirs or tanks made of high-density polyethylene, and the size is 3 meters in diameter and 3 meters in height, so we talk about almost 27 cubic meter capacity of each. And we had different ratios of mixing in those tanks. Just maybe you need to remember this slide very well, because all coming slides are related to those tanks. So the tank number 6 or pond number 6 basically was filled out with Dead Sea water. And the reason for that was to use it as a benchmark tank. What happens to each property in that tank? And we basically compare what's happening in other tanks with this tank. The next tank, tank number 5, basically was filled 85% with Dead Sea and 15% with rejected brine. Just we generated the rejected brine from the Red Sea water, and we added this to tank number 5. Tank number 4 basically has a ratio, this ratio, which is 10% Red Sea, 90, tank number 3, 2080, tank number 2, 3070, and tank number 4, 4060. As you can see, basically we have to create at least 4 points, okay, to judge about different types of different, let's say, data points of different ratios or different scenarios of mixing. Definitely, if we start filling the Dead Sea from now for, let's say, decades, we will not reach scenario number 1 where we're going to have 40% Red Sea. This picture basically shows the tanks. The tanks were placed very well, actually buried in the ground. And each tank basically is provided with a continuous flow of water through a baby tank, and the water is distributed in the wall through this cylindrical, or let's say a pipe that's placed in the top of the reservoir, in order to avoid introducing any mixing. So we left everything to be done as nature. The project lasted for 12 months and involved basically bi-weekly sampling, and the samples were collected at the top of each tank, in the middle, and at the bottom. So 3 samples were collected from each tank. Dust samples were collected twice, climate data from Arab Potash Company station, rain samples whenever we had rain, but unfortunately we did not have rain at that time. And salt core was collected at the end for gypsum and for actual analysis. So the first property to look at was temperature distribution through the tank, and you know how temperature is important in any water body and how important for different properties. Now, if you look at those 6 tanks, okay, it's tank number 6 again, where we have only Dead Sea water. Tank number 1, we have the highest ratio of mixing of Red Sea, 40% to 10, and tank number 5, which is 15% rejected brine, which is close to humidity. If you look at temperature distribution, eventually you cannot distinguish between the distribution at the top, while if you go to the middle, eventually you could see some segregations between those curves throughout the line, and it goes down and up. Definitely, this is driven by weather condition during the winter time. So in January, it's the coldest weather. So the vessel is affected by temperature actually in the atmosphere. If you look at the middle and at the top, the temperature distribution is almost similar, where the lowest temperature actually can be seen in the tank number 6, where we have only Dead Sea water. While in other tanks where we have high ratio of mixing, definitely the temperature is larger, which means mixing eventually results in generating some heat. This might be due to some type of, let's say, exothermic chemical reaction taking place in the vessel. Now, if we look at the acidity and mixing these two water barriers, okay, Vladimir, could you please mute your mic? Could you mute your mic, Vladimir, please? So anyway, so having two acidities with two water bodies, it's so important to keep actually the acidity or acidic behavior of Dead Sea water. And of course, if we look at it at the top of the tanks, the acidity eventually of the Dead Sea tank keeps going down, and the closest mixing ratio actually of rejected brine, it almost chases the behavior in the Dead Sea tank. The same thing is observed at the middle, and at the bottom you cannot really distinguish very well. So basically all tanks have a similar behavior with almost constant acidity, except the Dead Sea acidity keeps going down. Oxygen level is so important, especially for bacteria and microorganisms, and definitely for some other chemical reactions. Now, at the level of the sea, oxygen level is always about 9. And if you look at the top of those tanks, actually oxygen level is less, okay? And in the middle, eventually it drops significantly, goes to 2 milligrams per liter. And at the bottom, eventually is the minimum level of oxygen. Although we talk about a height of almost 2.5 to 3 meters, which means microorganisms could suffocate due to this low level of oxygen. Now, if we look at the density variation again is another property to look at, and density is significantly related to salinity, and of course it's function of pressure, temperature, composition of the vessel. And it's well known that water density of the Dead Sea or Dead Sea density is 1.24 grams per centimeter cube, compared to Red Sea, which is very close to fresh water, 1.0 to 180 grams per centimeter cube. Definitely mixing these two bodies will change the density. As shown here at the top, the density actually of the Red Sea water starting from the start of the project is increasing and rocketing up, okay? And followed by rejected brine density, although we are talking about the top part of the vessel. And the middle, again, the rejected brine is almost constant, does not change much, because you remember a rejected brine tank basically is filled only in the top part, which is 15%. And other tanks, if we look at other tanks, and tank 1 where we have 40%, actually the density is even decreasing and going down almost to the density of fresh water. And at the bottom, all densities eventually cluster to almost the same value, except that Dead Sea water density goes up. As I said, density is related to total dissolved salts or total dissolved solids, where we have in the Dead Sea almost 35%, and the Red Sea is 4%, okay? And of course, this can be measured in terms of electrical conductivity. And you can notice in here a comparison between the 7 lakes in the United States, where basically the majority of salt or large amount of salt is created in a Great Salt Lake, okay? So where this Dead Sea is located, if we compare it to those, let's say, lakes, definitely the Dead Sea actually has much more salinity than the Great Salt Lake. So salinity goes up to 330,000 ppm. So again, the salt concentration here eventually behaves in a similar way to density. And if you just map these two figures, you could see very small discrepancies where the rejected fine tank is almost following or getting as close as possible to the Dead Sea tank. Well, viscosity actually in here we have two fluids, okay, Red Sea and Dead Sea. So Dead Sea is more viscous actually than the Red Sea, and higher viscosity definitely might slow down the diffusion processes and natural, let's say, convection or frictional effect in terms of mixing. So the viscosity at the top, as you can see here, is going up for in the Dead Sea tank. And the next tank that behaves similarly or closely actually is the rejected fine, then the this ratio. In the middle, eventually many tanks have similar behavior, and at the bottom, okay, the one that can be distinguished from all other tanks is the Dead Sea, while all other tanks in terms of viscosities behave the same, okay? Turbidity, this is another property that we basically look at, and just to see is an indicator about the total suspended solids, okay, whether we have suspended, let's say, salts. The turbidity measurement eventually was quite low, less than 19 MTU, which is the maximum for the sea. Water actually was very clear. You could see the bottom of the vessel. And the other property, which is biological oxygen demands, again, this is related to microbial activity in the tank. And we could see during the initial or during the first basically half a year, actually we have some large values of POD. And this is an indicator of not having enough oxygen, which means the system requires more oxygen. And then as we went further during the half or the second half year of the project, so the level eventually went down. And usually POD goes up to 4 milligrams per liter or 2 milligrams per liter for C. Now, if we look at all those properties in terms of vertical variation, let's start with the temperature here. What one can notice, okay, we can notice that the temperature profile is changing for all tanks, but the Dead Sea tank. So the Dead Sea tank temperature profile is linear, so throughout the tank, while in other tanks, eventually the temperature does change. Okay, so in other tanks, as you can see, so the temperature eventually does change, and we have a transition in the middle part in terms of temperature distribution. Okay, so what does this mean? This means that we have two types maybe of diffusion. Maybe in the top part of the tanks, we could have convective flux, while at the bottom part we have diffuser. And in the middle, this is an area of certainty where we could have combinations of two types of diffusion. So later on, if we take different times of the year, what can we see actually? This is in April. We can see the gap between top and bottom eventually is narrowed in terms of temperature variation. If you compare it with, let's say, between October and September, so one can see this beta. And basically the gap actually in October 2008 was almost 25 degrees, while in June 2009, the gap is almost 20 degrees. So the gap between temperature variation goes down. The same trend actually was observed with respect to density. So in this figure, we can see that the density variation in the Dead Sea tank is constant, while in all other tanks we have again two regions for densities. So we have the upper and we have the lower, and we have a transition in between. So again, which tank is behaving closely to the Dead Sea benchmark, okay, is the rejected brine tank. If you compare different time frames, what we can see, the rejected actually brine tank is trying to get as close as possible in terms of density distribution to the Dead Sea tank. So the next one actually is bacterial growth, okay? And bacterial growth was observed during the initial maybe 6 months or 5 months, okay? And it was observed only in the tanks that have higher ratios of mixing. Tank number 1, tank number 1, 40-60, number 2, 30-70, and number 3, 20-80. And again, in the second half of the year, what we observed actually some bacterial growth only in tank number 1, where eventually no bacteria could be observed in other tanks. And of course, different types of bacteria were observed. And the most common one that was seen under the microscope is, after culturing, of course, is a gram-positive stack shade, where we have basically like capones in blue and in violet in color, and they cluster themselves like a grape. Other types of two bacteria, okay, which is with traces, okay, is a gram-positive and gram-negative acidic bacteria. So, as I said, we will take care of dust as well. So 2 samples of dust were collected actually in per 1 meter square, and the size of the first sample or the weight of the first sample is 6.23 gram. Okay, of course we cleaned the vessel at the very beginning of the project, and this was collected in February, okay, 2009. And in December 2009, another sample was collected, and this is the XRD analysis actually for those 2 samples. And you can see we have some variation in the metal oxides of different actually dust samples. And of course, it was increased by the end of the project compared to the middle. Although the time interval is almost the same, one can notice that the phosphate concentration eventually is increased almost by 20% or more. And as you know, phosphate could be a good nutrient for bacterial growth in the tanks. The other one is gypsum. Gypsum was collected using actually a BB syrup that was inserted in each tank. And we actually collected those rods at the end of the project. And the one that is shown here, actually taken from the Dead Sea tank, as you can see, basically we have mainly salts. And in the rejected brine tank, we have salts and gypsum. We have minimum amount of gypsum actually and salts that were deposited in the surface of other rods. These actually were taken and XRD was carried out. And of course, it showed peaks for gypsum and for other minerals. And when we look at the chemicals that are most important for, let's say, potash industry, is halide that is converted later into bischofite through evaporation. And at the end, they get their basically needed source material, which is carnallite. Now what we observed as per the analysis using whatever collected or whatever samples collected, in the top of tank 1, actually top of tank 2, 3, etc., for 5 tanks, and the middle of the tanks and at the bottom, halide is the major element actually in all tanks, and bischofite was major and minor, and we have some traces of carnallite showing up. Now, as time goes on, we expect bischofite to get less and to get converted into actually carnallite. And course, let me skip those slides in here. But to summarize the peaks obtained for gypsum, the peak intensity was the largest in tank 1, 40 to 60% ratio of mixing, and it was the lowest actually in tank 4, which is 10 to 90. While gypsum peak was larger when we have rejected fine mixing with the Dead Sea is 550. Well, no peaks were detected for the Dead Sea because of the absence of sulfate. Now, in terms of chemicals, okay, hopefully I have a bit of time to go over. So, chemical speciation with respect to halide, okay. So, halide eventually at the top of the tank, which is so important for industries because this is their main raw material. So, actually in the Dead Sea tank, halide concentration eventually is decreasing, okay, because of, as I just mentioned in here, it gets converted into bischofite and then into carnallite. And if we look at the other tank where we have rejected fine, actually it does follow similar trend, which is desired here to have, because it means actually in this tank we get more halide converted into bischofite. While in all other 4 tanks, yes.
Just 2 minutes extra to.
Okay, no worries. Thank you so much, Department. So now, eventually, what can I say? Because when Dr. Adnan talks, I have no other choice but to listen. So, in terms of trend, this was observed at the top and the middle. Other chemicals eventually have similar trends. Okay, so and of course, this creates some concerns. Okay. So if you look at the calcium chloride in here, so basically similar trends between rejected fine and Dead Sea tank, while at the bottom, all tanks eventually behave the same. So we care a lot about halide. Now what happens to rate of evaporation after finishing the 1 year of vigilance? What we decided to do, we said, well, we stopped feeding those tanks from the baby tanks, and we looked at the level decline. What one can see from this figure is that the level decline actually is the lowest in the tank that has Dead Sea water, while basically the next tank is the one with the rejected fine, okay? And of course, the level decline is the highest when we have 40-60%, which is expected because the Red Sea water is closer to Dead Sea water in terms of property. To wrap up my talk in here, so we actually observed many things that did take place in those 6 points. First, stratification does take place in terms of all major properties where we have vertical variation. The other thing actually we observed is basically some microorganisms could survive, and of course we have continuous feed to the sea. Of course, if the Iberian country is going to go for, let's say, continuous flow of Red Sea into the Dead Sea, definitely bacterial growth is an issue for industries. The other one is the gypsum crystallization due to high rate of sulfate and high rate and calcium, of course, potassium. Of course, there is an issue, and if they become heavy and sink down, definitely they will affect the point of intake of those industries and pumping efficiency. Definitely, the effect is dramatic and significant, but this effect can be minimized if only rejected fine is to be conveyed to the Dead Sea. And point of entry is another issue to look at definitely, not to have it as close as possible to point of entry. Only recently we got approval to publish what we actually noticed. So 2 papers already appeared. One is used as a benchmark, for the Dead Sea itself, and one is describing the change in physical properties. Another one is underway about changes in chemical, and 2 or 3 other papers definitely will be published from this project. This project was a teamwork, started actually back when I was at Mecca University, and my colleague, Dr. Mufid Patasa, who is working for Abu Dhabi Polytechnic right now, worked with us, and 3 team members from Arab Research Company, Jamal Amira, Khalid Nawisa, and Talat. Definitely, this project could not be possible without the general support of Arab Research Company at that time. So I want to thank them again, and whenever I talk about this project, I have no other choice but to thank them, and to thank you for being so patient to listen to this short and quick topic. Actually, I need maybe at least 1.5 hours to talk in details. Anyway, thank you so much for having me today, and I will be more than happy to answer any question or to listen to any comments and suggestions.
Thank you, Professor Abdulaziz Khifat, for your excellent presentation, highlighting the critical situation around the sea. Due to the shortage in time, we will have 1 or 2 questions. Questions, please. Please. شكرا دكتور خليفة على الإيضاح المنوع الصحيح على الوضع الخطير المقبل عليه البحريين. شو الحلول اللي مقترحة أو اللي تتصور هي راح تكون حل لهذا المعضلة اللي متوقع تصير سنة 2030؟ شكرا.
Thank you so much. Actually, I'm not a politician, and I don't think I can answer this question. But the best solution eventually is to stop, hurting the Dead Sea in terms of harvesting. If we go back to whatever given by nature and let it flow, then definitely we will have no issue. Now, if we look at what have been withdrawn from the feeds to the Dead Sea, the purpose behind that was drinking water. And I don't think if a country has, let's say, a border with the sea, can talk about water scarcity. Unless this country has, let's say, bad management when it comes to water. And so many countries, even if you go to the United States, for example, California, they have lots of groundwater, yet they desalinate water. So I believe for drinking purposes, water desalination is the most viable choice. And if you look at Jordan, have done these projects, dams, for the sake of having drinking water. Now, if the drinking water issue is resolved, okay, then I guess the flow of natural streams actually can be restored, and definitely the level can be restored as a function of time, instead of creating some other problems. Because usually, if you, as I mentioned here, if you replenish the Dead Sea with fresh Red Sea water, definitely you create lots of problems, and you affect the existing industries as well. And of course, you change the composition of the Dead Sea water itself. I did not talk about this because it is used for other purposes, whether it is medicinal or others, okay? So the cheapest choice, I would say, is to desalinate, for example, for Jordan, to desalinate the Red Sea water, maybe in Aqaba, and to forget about this canal completely, and to let water flow from those constructed dams in the eastern part. And the same thing has to happen in the western part. I believe this is the most viable option. And then, if we, let's say, have a canal to carry out or to convey the water to the Dead Sea, definitely we will have issues to maintain it, and we might face some issues. So I don't want to dig deep into politics. I'm not a politician, so I can talk about, academic issues more.
Thank you, Dr. Abdulaziz, for being with us this afternoon, and we hope to see you soon here in Jordan. Thank you very much.
Inshallah. Thank you so much and have a nice afternoon. Stay safe. Thank you.
Assalamu alaikum, yatiku alf afia. Good afternoon, everyone. Thank you very much for coming back to the next half, or to the second half of Chemical Engineering Kinetic. And I would like to present our first speaker for this afternoon, Dr. Ayman Awad, who will be talking about MBAS, removal by natural zeolite adsorption, isotherm kinetic, and thermodynamic study. Dr. Awad is a professor in chemical engineering, or professor of water and environmental engineering at Middle East University, Civil Engineering Department. He has a bachelor degree in chemical engineering from Jordan University, and then a master degree in water and environmental engineering, Civil Engineering Department 2008. And he has a PhD in environmental engineering from UNESCO Chair for Water Resources, Sweden, 2014. Dr. Awad, the audium is yours. You can start. Thank you.
Thank you, everybody. Good evening for you all. I hope that you will be take a lot of information about our subject today. Our subject today is about to remove the contaminants from the wastewater. And you know that Jordan, one of the poorest country in the water issue. No. طيب ماشي هاي فلاش اوكي ايوه افتح لا اللي فوقيها لا افتح الفايل معلش شوي على هاي ايوه زي لايك والثاني هاي لا هاي ايوه اوكي حطيتها على الديسكتوب Okay. You know that many industries have a lot of contaminants, and those contaminants go to the water or pollute a huge amount of water in the industry. So our target here to remove or to get rid of the contaminants. The story of our research here, and me and my colleagues, and how to get rid of what is called MBAS. MBAS is the method of measuring the contaminants of the surfactant ionic substances, which is the didecyl benzyl sulfonate, which is used in the detergent industry. So a lot of those contaminants reach the water. Okay. And as usual, we start with the classical procedure or steps to treatment the wastewater. The wastewater which we are dealing with, that one is collected from different sites or different stations in Jordan here in Amman city, and mixed well to form a homogeneous solution. After that, let me go what we will show in the presentation. We will start an introduction, I said before. Then the previous study, I talk about the previous study. Now I will clear the previous study. As I said before that, we start to treat the wastewater by classical or the traditional methods, which is the sedimentation followed by flotation and again by filtration, sand filtration, and we found that the removal efficiency is minimal. So when we get these results, we decide to go for more and further investigation by adsorption. We will see the objective of this research, or this work, literature review, materials and methods through the natural zeolite, sampling, absorption isotherms and kinetics, absorption performance indicators. The articles we use them to analyze the process of the removal, and finally the thermodynamics studies. All of these things give our results and discussion through the most famous models for predicting the mechanism of the removal, which is at the end, it was the adsorption. And finally, the conclusion. So if we look at the introduction, methyl blue active substances, it is the method to measure the contaminants, which is didecyl benzyl sulfonate, surfactants, contaminants, which is most common pollutants in the wastewater. As you know that contaminants or these contaminants are serious, have a serious impact on humans, animals, and the plants. When it reach the water, it will be polluted, a big quantity of water, so produce a toxic effects in aquatic organism. The standards or the threshold value or the reference of those contaminants in the wastewater must be lower than 25 milligram per liter. This is our story, as said before, about our research, which is those are the steps. Those are the steps which we are done upon the wastewater, and this is our results here, and you see that the removal efficiency for the impasse contaminants is stopped at about the reduction in removal efficiency, it's about 5%, 10% by the classical or traditional treatment procedure. After that, as I said before, we started to think about the adsorption. We applied the adsorption by using natural zeolite. When we use the natural zeolite as an adsorbent, we prepare that adsorbent by crashing, washing, soaking in nitric acid, diluted nitric acid to get rid of volatile organic compounds, and any impurities can be oxidized by this system. And finally, we prepared a set of experiments with different adsorbent dose. Our adsorbent dose were 0.1 gram of the adsorbent, 0.5, and finally 1 gram. A lot of experiments were done to go through the removal efficiency and the contaminant uptake. To study the thermodynamic properties of those removal of the contaminants, we did the 3 experiments at 3 different temperatures. There were 25 degrees, 35 degrees, and 45 degrees. And the results will show the results later. Okay. This is the literature review, and you know that during such work that many researchers did a lot of researches and tried to modify the adsorbent, especially we're talking about the natural zeolite to change it for modified or something like this, and they brought a lot of recommendation and results for the researchers after them to use it. Those are a lot of literature reviews here. The proposed treatment, I said before that we stop here and think about to study the batch equilibrium technique. We use, excuse me? We did the batch equilibrium techniques for the system of natural zeolite and base contaminants or surfactants, didecyl benzyl sulfonate contaminants with the natural zeolite at the step 5, as I said before in the proposed treatment plant, and different system of treatment were prepared. And again, this is the natural zeolite, as I said before, prepared well in those steps or those procedure. Sampling, as I said before, we started all of our samples at initial concentration of 19 milligram per liter here, and adsorbent dose, 3 adsorbent dose. So the system, our system here is the contaminants, natural zeolite at initial concentration of 19 milligram per liter, and 3 categories of adsorbent dose of 0.1, 0.5, and 1 gram per liter. The study of absorption isotherms kinetics studies, we used 3 models actually. The first one is Lange-Muir model, and then the Freundlich model, and finally the Besido second order model. Why we choose those are the common models used to testing the fitting of the results of the experiment in such work. Again, we used those performance indicators to calculate the removal efficiency or the uptake efficiency and uptake capacity, and finally the partition coefficient, which is indicate the combination or the adhesion of the adsorbent with adsorbate. Again, the thermodynamic studies can be analyzed the three type of energy in such chemical or such processes, which is the entropy, enthalpy, and Gibbs-free energy. And we use those equations to calculate those type of energy. The error in the analysis can be calculated from whether the mean square error equation, this one, or the chi-square testing, as you see in the slide. Those are our results and some discussion about the results. Here from the uptake efficiency, it is found that the maximum uptake efficiency of zeolite was 93.42% using the initial concentration of 19 milligram per liter, and the final concentration we reached 1.25 milligram per liter after 120 minutes. Actually, if we look to this table, we find that something interesting, that most of the removal efficiency was in the beginning or in 5 minutes. But for more investigation and more emphasize that there is more significant removal, we try to go for or go in elapsing of the time of the experiment to ensure that most of the removal efficiency was done in the beginning of the experiments. And this table is constructed from one sample of testing, which is at 1 gram of adsorbent dose. And we find that the parameters for the models, the isothermal models, Langmuir, and we used four types of Langmuir model, which is the first order, second order, third order, and fourth order. And we use, as I said before, the Freundlich isotherms model and Besido second order model. And all of these parameters used to check the fitness of the data according to those models. In effect of the temperature, we found that there is no. Okay. The effect of temperature on the removal efficiency was insignificant, as you see in the slide, that there is a minimal or small removal efficiency between 25 degrees and 45 degrees at about 6.22 milligram per gram, and this is an uptake capacity, not capacity removal or removal efficiency. This means that the dominant process or the dominant procedure or the dominant mechanism removal is the adsorption. Again, isotherm studies, and you see that the correlation coefficients of all of the models about 0.99, something like this, which means that the data fitted by all of the models, but actually the most accurate one is the Besido second order model. Again, those are the models, and those are the removal efficiency, Freundlich model analysis. And this is the Besido second order model fitting. You see that the correlation coefficient here at adsorbent dose of 0.5 milligram is 1. And again, the thermodynamic studies, as I said before, that there is insignificant effect of the temperature on removal efficiency. And finally, the conclusion, Actually, this research is about to examine the suitability of the natural zeolite for removal of those type of contaminants. The study includes the determination of the specification, the adsorbent, which is the natural zeolite. The removal efficiency is achieved within the very short time in all experiments done. The removal efficiency is ranged from 75, as we saw in the table, up to 93% of the initial concentration. The removal efficiency increased with natural zeolite adsorbent dose increases, contact time increases, temperature increases, and the initial concentration decreases, which is usually happened in this type of investigation. The isotherm study showed best fit on Langenmuir and Besido second order models, while Freundlich model has a slightly different value in correlation coefficient, actually. The maximum uptake capacity obtained from Langenmuir model increased from the 25% up to 31% of the temperature as the temperature increased from 25 to 45. The Besido second order model presented that the best fitness for the experimental data followed by Langenmuir model. It is obvious that the distribution coefficient, LKD, increased with the increasing in the temperature, and the high KD values indicated that the higher amount of impasse had been retained by the adsorbents. Finally, according to the result, it could be recognized that the natural zeolite can be used effectively to remove impasse contaminants from car wash stations wastewater with a high efficiency up to 93%. Thank you.
Thank you, Dr. Ayman, for your valuable talk. We have just a room for one quick question.
Thank you, Professor, for this nice presentation. Actually, I don't have a question, but I have suggestion, because I worked in zeolite before for hydrocarbon removal from water surface. I used Jordanian zeolitic tuff from Tal Hassan. So I tried to, since you are aiming to remove surfactant, so I suggest for you, or if you want to continue in this research, to increase the hydrophobic properties of zeolite by manipulating aluminum to silicon ratio, or by, I did that by acid treatment, or by attaching surfactant into the surface of zeolite. By this, you increase the hydrophobic properties, and you can get 100% removal, and the sorbent can be regenerated and used at least for 5 cycles. Yeah, thank you.
Thank you very much. Okay, our next speaker is Dr. Ziad Abu Rob, and he will be delivering his talk about kinetics of toluene dry reforming reaction using Jordanian kaolinite as a catalyst. Dr. Abu Rob is an assistant professor at the German Jordanian University, and his current research work encompasses catalysis in biomass gasification, oil shale, and wastewater treatment. Dr. Abu Rob holds a PhD in chemical engineering from the University of Twente, and he is a consultant engineer in bioenergy. Dr. Abu Rob, the mic is yours.
Good afternoon, everybody. I hope the voice is loud and clear. I hope everybody is also awake after such several long presentations. I'll do my best to make my presentation concise and short. So my talk about kinetics of toluene removal via dry reforming reaction using one of the Jordanian minerals as a catalyst. The content of my presentation is, as any research topic, is introduction, followed by the objective of this paper, and then the methodology, results, and conclusions. Let us start first with biomass. My area of research focuses on thermal conversion of biomass via catalytic conversion. So, and why we focus on biomass? Because if you look to the primary energy sources, more than 80% are from fossil fuels, which enhances or increases the carbon dioxide and greenhouse emissions, which is environmentally harmful. Whereas the biomass is only 14% and the rest is nuclear energy. So we are looking for capitalizing on more means to harness the energy stored in the biomass. One of the technologies that is really important and very common is gasification technology, is the second technology after combustion. Combustion is well known. However, the disadvantage of this technology, even though it is well understood and commercialized, is its low efficiency, relatively speaking, like 20%. Whereas gasification technology still is not commercialized well, but the advantage of this technology is the high efficiency, especially if it is integrated downstream. It could increase up to 40%. So this is why the interest in biomass gasification. Now, gasification is partial combustion of biomass. The idea here is you produce a gas that has a heating value, and then this gas can be converted into electricity, fuel, chemicals, etc. So this technology still needs some more research. However, this gas that is produced has some drawbacks. Most importantly are tars. I will talk about them a little bit later, particulates, and inorganic trace elements. Now, what is the tar? In that gas, which is we call producer gas or syngas, it composed mainly of carbon monoxide and hydrogen. Both of these gases can be combusted, thus they have heating value. But with this gas, we have some heavy hydrocarbons. We call it tars. These tars, it's a general name for any hydrocarbon heavier than benzene. We call it tar. So tar creates so many problems. Like, as you can see here, first of all, if you remove it, you reduce the heating value of the gas. It can condense, make clogging, many interruptions in the process. So we have to get rid of the tar. Now, if you look to the composition of the tar, you could see like benzene is almost 40%. The second component is toluene, the third component is naphthalene, and the rest are hydrocarbons. And it's very important now to study the behavior of tar interactions through the behavior of these components. So instead of studying this complex mixture, we can select certain components that can mimic the behavior of the whole spectrum. And most of the research focus on either naphthalene, benzene, toluene. In my study, I focus here on toluene. The most important reactions that can convert the tar, as you can see here, are steam reforming, where we react the tar with steam, so that we produce the syngas, which is carbon monoxide and hydrogen. The second reaction is dry reforming. That means we react the tar with only carbon dioxide. And the third one is thermally cracking, especially at elevated temperatures, more than 1,000 degrees Celsius. In a nutshell, this is an overview of this biomass gasification. When I say biomass, biomass is also a generic word that encompasses different types of biomass, like waste, municipal solid waste, and others. Here you partially combust the biomass to produce the gas, and then we have different ways of removing the tars, either physical separation or catalytic conversion or thermal. My focus here is on catalytic conversion so that I can use less temperatures, which is economically more viable. So here I need to find a good catalyst that can convert the tar into light gases so that I don't lose the heating value in the gas. Another problem with the biomass gasification or the syngas is the high percentage of carbon dioxide. So my idea here, if I can use a catalyst that has good catalytic properties, cheap, and at the same time focus on reacting the tar with the carbon dioxide to produce light components, gas components with heating value, I hit more than one bird with one stone. So I look for Jordanian minerals that could be a potential catalyst for tar removal. So one of the potential minerals is kaolinite. Kaolinite is basically an aluminosilicate, and it's available in many locations in Jordan, as you can see from north to south. Okay, and at the same time, this aluminosilicate contains also some metals, especially alkali metals and transition metals, and these can act as promoters for the catalytic reaction. So this was my investigation, is how this material can be an active catalyst in the raw form, and in the later stage, we will do some modification on that material to alleviate the catalytic activity. In a nutshell, my research focused on getting rid of carbon dioxide by getting rid of the tar by reacting it with the carbon dioxide using kaolinite as a catalyst, as a Jordanian mineral which is available abundantly, so that I convert this into light gases. How to measure the activity of this material is by finding the kinetic constant, which is the apparent kinetic constant. So I first did some characterization for this material and then did some tar measurement for the tar conversion at different temperatures in order to find the kinetic constant. So I did first characterization for this material, which I brought from Al-Hassa deposit. I did some TGA, BET analysis, and XRF analysis. This is the setup I did the experiment on. So I made a synthetic gas that is composed basically from nitrogen, and I fed one of the nitrogen streams into a saturation unit filled with toluene, so that another stream of nitrogen here can create the right mix and the right composition, and together also with CO2 gas. All gases are mixed together on top, and then they pass through a catalytic bed of kaolinite, and the bottom output goes to gas analysis, which I use here, gas chromatography with 2 detectors, thermal conductivity detector, and flame ionization detector. This is the setup I used in my lab. The operating conditions I used, the temperature range is the catalytic range, which is from 750 to 900 degrees Celsius. The pressure is atmospheric. The gas residence time is 0.3 seconds. And the feed composition is mainly carbon dioxide, 20%, and nitrogen, 20%. And the toluene concentration is 10 grams per normal meter cube. The kinetic model I used here is basically, if you look to the first equation, is second order, but because I fed carbon dioxide in high concentration, that means the change in the concentration of carbon dioxide is negligible, so it can be considered as constant. That's why I call it pseudo first order. Here, that's why I used the apparent kinetic constant, and usually heterogeneous reactions are considered first order. So that I calculate via computing the input and output concentrations. I could calculate now the conversion, and from the conversion at different temperatures, I calculate the kinetic constant at each temperature. And then I use Arrhenius equation so that I can calculate the activation energy and the pre-exponential factor. And especially the activation energy is very important in order to distinguish the catalytic activity. The higher the activation energy, the lower is the activity usually. So this is the simple model I used. For the thermographic analysis, I used this instrument. And here you could see from room temperature to 900 degrees Celsius, how much we have weight lost. And we could see that at different heating rates from 10 to 100 degrees Celsius, we have on average 12% reduction, especially which is dehumidification of the aluminosilicate. The second test we did is the specific surface area. And here we measure the effect of heating rate on kaolinite evaluated surface area. And you could see an interesting result here. The higher the heating rate, the lower the BET surface area, and which could be related to, at high heating rate, we have strong escape of gases that could break the pores. And as a consequence, then you have less existing or produced surface area. The third test I did in the characterization is the XRF, and I use this instrument. It's for Pioneer. And here we could see the major metal oxides in the kaolinite. And you could see that the Jordanian kaolinite has mainly silica, alumina with ratio 2:1 almost. And the interesting thing also is we have to look on the alkali metals and the transition metals in this mineral, because as I said, they have some catalytic activity as they work as promoters, especially the potassium oxide and the iron oxide. We also measured, studied the reactions that are happening there by making gas chromatography for the input and output gases at the different temperature. So as I said, I used the gas chromatography 2 detectors, flame ionization detector for targeting the organic components, and thermal conductivity detectors for targeting the inorganic gases. And at 900 degrees Celsius, for example, you could see the peaks from the flame ionization detector. We could, I think the text is not clear, but we have xylene, benzene, toluene, and methane from the flame ionization detector. Whereas from the thermal conductivity detector, we could detect CO2, CO, and hydrogen. This is the hydrogen peak. The second is the CO2 peak. The fifth is the methane, and the sixth is the carbon monoxide. So basically from calculating the peak area, we could calculate the concentration, and from the concentration, we calculate the conversion. And this is the results we got for the conversion. The higher the temperature, the higher the conversion. And then we calculate, as I said in the model, the kinetic constant. And from plotting ln K versus 1/T, we can find the activation energy and the pre-exponential factor. And we find that the activation energy for kaolinite as a catalyst is 209 kilojoule per mole, whereas the pre-exponential factor is 5.86 10 to the power 9 per second. So in conclusion, we could find that dry reforming reaction and also catalytic cracking both happen, because we could see some black color on the catalyst bed. We found the activation energy and the pre-exponential factor, and the BET surface area and the effect of heating rate on the BET surface area. The BET surface area of the kaolinite was found to be like 18 meters square per gram. And if we look to two factors here, the activity of kaolinite at such temperature, which was 80% at 900 degrees Celsius, and also the physical rigidity of kaolinite as that can be used as a fluidized bed material. If you combine these two advantages, This makes kaolinite as a strong candidate as a potential catalyst for tar removal, especially if we want to enhance its activity by impregnating some transition metals on the surface of that catalyst, then we could achieve even higher convergence. And this brings me to the end of my presentation. Thank you very much.
Thank you, Dr. Ziad. Any question? No. On.
Sorry? مش فاهم، مش سامع. Actually, so the lifetime of this catalyst before that it stay as active material, we did not study that. Why? Because at the stage in time, at this phase of our experiment, it's not important. Because this very inexpensive material, it's not like, for example, a nickel catalyst, which is expensive, or some catalyst with transition metals. But if we start improving the activity of this catalyst by impregnating some transition metals, then we will, of course, consider the regeneration of the catalyst rather than just bringing new batches of this catalyst. Okay, thank you very much.
Thank you, Ziad. Our next speaker is Sharon Pereira, who is joining us via Zoom from India. And Sharon is going to deliver a talk about application of modified Langmuir-Friendlich isotherm for modeling chromium adsorption at varying pH conditions. Sharon, are you with us? Sharon? Do you hear me? Okay, in this case, we have to skip Sharon and go to the next speaker, Shakir R. Kolkani from Saudi Arabia, who will be talking about spray drying synthesis of oxidative coupling of methane catalysis, inclusion of SIC to the support. Shakir, are you with us?
Hi, yeah, can you hear me?
Okay, the screen is yours. You can start now.
Okay. I think it's not allowed. I'm not allowed to share my screen by the host. Yeah, I cannot.
Shakir, can you please share the screen from your side?
Yeah, it's not allowing. It says that the host
and your voice is not
enable
clear.
the. No, I cannot. Can you see it now?
Shakir, your screen is shared now, but can you please get it close to your mic so we can hear you well?
Sorry? Hello? Can you hear me well now?
Yes, you can start, Shakir.
Shall I start?
Can you start, please?
Yes. Well, I need to clarify that it's not Shekar making the presentation. My name is Wansal. I work with Shekar, but it's finally me giving this presentation. Okay. Having said that, thank you, Mr. Speaker, for introducing me, and I will be showing today our work related to spheroidal catalysts for the oxidative coupling of methane. The oxidative coupling of methane is a reaction that aims to convert methane into valuable C2 chemicals in a single pass. It's a very exothermic reaction, but it's not equilibrium limited, mainly because it's a partial oxidation. However, in this interplay of oxidation, the undesirable deep oxidation to CO and CO2 can also happen. The interest of OCM is basically replacing current production routes of light olefins, which is mainly steam cracking, and at the same time easing the conversion of methane to valuable chemicals, which is also done these days by very numerous and energy-intensive pathways. Although despite from the stoichiometric equations, one could think that the OCM is a very simple reaction. That is not the case. As we all know, the CH bond in methane is the hardest of all the hydrocarbons, and therefore a high energy input is required to break that bond. Therefore, in the reactor, high temperatures are required, and under those harsh conditions, the catalyst tends to sinter and therefore deactivate. At the same time, the oxidative coupling of methane is a reactive system where we have a combination of gas phase homogeneous reactions and solid catalyzed surface reactions. Therefore, it's also a very difficult reaction from a mechanistic point of view. Since the discovery of the OCM in the early 80s, only a few or almost no catalysts have been reported with the desired C2 carbon yield, which should be over 30% for the industrial scale-up of this process. Therefore, the development of catalysts is a core challenge for the OCM. One of the benchmark catalysts that are studied for the OCM is the trimetallic system containing manganese, sodium, and tungstate supported onto silica. It is well known that manganese boosts surface oxygen mobility, which enables an easier activation of the methane. Sodium, on the other hand, facilitates the transition of amorphous silica to alpha cristobalite, which is inert and avoids the unselective oxidation of methane. The role of sodium is that it decreases the transition temperature from around 1500 degrees C to around 700 or 800 degrees C. At the same time, tungsten typically forms the sodium tungstate, which is a recognized active phase in the literature. With this trimetallic catalyst supported onto silica, typically around 20 to 30% methane conversion and 60 to 80% C2 selectivity are attained. However, as I mentioned before, it is fundamental that the performance of these trimetallic catalysts are enhanced. There are many avenues for enhancing performance of catalysts, of course, but one of them is studying the different supports or proposing new supports. In this regard, many efforts have been made in the literature, and a wide variety of supports reported for this catalyst include changing the silica source material for the support, or proposing other mesoporous silicas, oxides of many types like alumina, titanium, zirconia, and so on, and even zeolite. However, we think that the inclusion of silicon carbide can provide multiple benefits, and therefore, in our study, we consider the modification of the support by including silicon carbide. In previous studies, as you can see in the slide, silicon carbide has been fully replaced. Silica has been fully replaced by silicon carbide, and as it can be seen, enhanced stabilities were reported. At the same time, with silicon carbide monoliths, a decrease in actual temperature gradients were also reported. This is obvious because due to the physicochemical properties of the silicon carbide with enhanced thermal conductivity, this kind of phenomena are expected. However, there's no study that has addressed the role that a silicon carbide plays in the OCM, and at the same time, all the studies that included silicon carbide in the support have replaced fully the silica. Therefore, we believe that the incorporation but not replacement of silica and silicon carbide could give several benefits, and therefore we propose a novel manganese sodium tungstate catalyst supported onto a mixture of silica and silicon carbide. In this study, this catalyst has been prepared by a more novel technique, which is spray drying compared to common impregnation. In spray drying, the slurry precursor is atomized and afterwards dried to form particles that of a very well controlled size and morphology. In fact, through the control or tuning of the settings of the spray dryer and the operating conditions such as chamber drying rate or atomizer aperture or flow rate of carriers and so on, the final properties of the particle can be very well tuned. At the same time, another benefit of spray drying as a synthesis technique is that it's versatile, cost-effective, it's a continuous process, and therefore, from an industrial scale point of view, it's scalable and even reproducible. So, in the present study, two catalysts were prepared: the spray dry catalyst that I just mentioned, and another one prepared by impregnation of the metals onto silica, pure silica, so that it acts as a benchmark catalyst, and therefore we can compare the results. From hydrogen TPR results, we can see that the spray dry catalyst or the reduction peaks associated to manganese and tungsten species in the spray dry catalyst were shifted to higher temperatures compared to the impregnated catalyst. At the same time, the spray dry catalyst showed a higher hydrogen intake, meaning that it's more reducible. These differences one could attribute to different, for example, metal-sapone interactions that silicon carbide, that the inclusion of silicon carbide may provide. However, the nature of silicon carbide does not, or typically does not account for those, and therefore we believe that it's more related to differences in dispersion and morphology of the phases. From high-resolution XPS spectra, we could confirm that for both catalysts, the Mn3+, Na1+, Si4+, and W6+ species are present in the surface. We could also confirm that a relative surface composition of both catalysts was rather similar. However, by analyzing the CO1s spectra in the spray dry catalyst, no peak associated to silicon carbide could be observed, and therefore we conclude that the surface must be silica enriched and the core must be silicon carbide enriched. From scanning electron microscopy results of the spray dry catalyst, we can see that synthesis particles had a very well-defined spherical morphology with silicon carbide smaller subparticles. For Raman spectroscopy, we determined by pointing the laser at different positions of the particle that there is a uniformity of the phase. These features we attribute to the utilization of a spray drying as a synthesis technique compared to the impregnation catalyst. It is also to be mentioned that through this Raman spectroscopy, main phases such as the aforementioned sodium tungstate or even manganese tungstate and brownite could be observed, as well as the cristobalite required for the reaction. As for the kinetic results, first of all, we changed temperature in our fixed reactor. We tested both catalysts and even a blank at different reaction temperatures, and we could see that.
Mr. Kulkarni, can you hurry up, please?
Oh, sure. So we observed that there was only remarkable activity at temperatures beyond 750 degrees C. However, by looking at the right-hand side of the slide, we can see that from the solid symbols that both catalysts presented a similar activity and selectivity. So then, where's the catch of the more novel spreader catalyst? Well, when we studied when we performed time on stream analysis, we observed that while the impregnated catalyst underwent severe deactivation with 66% of the residual activity after 70 hours, the spreader catalyst was perfectly stable, retaining almost, I think, 90% of the residual stability. In order to assess the nature of this phenomenon, we performed XRD and gamma spectroscopy spectra of both catalysts and in fresh and used samples. And we could observe that in the used samples, in both catalysts, cristobalite was transformed to quartz. But the most remarkable finding of this study was found in the Raman spectroscopy, where a clear distinction between the active phases of both catalysts could be observed. Where for the spreader catalyst, manganese tungstate and brownite were detected compared to the impregnated catalyst, where the very well-known sodium tungstate was identified. Therefore, we conclude that the enhanced stability that
Mr. Kulkarni, you have 1 minute, please.
Yes. So we could conclude that the extended stability that the spreader catalyst showed was attributed to the presence or to the alteration of the active sites that the silicon carbide provided. So all in all, we synthesized a catalyst through a more novel technique, including silicon carbide, that through the more uniform morphology, enhanced thermal conductivity, and modified active sites, provided similar activity to the benchmark catalyst, but extended stability. And that's the end of my presentation. Thank you very much.
Thank you very much. Due to the time limitation, we have to go to the next presentation. And Khairallah Naeem Ahmed, Dr. Khairallah Naeem Ahmed, are you with us?
Okay, thank you.
Yes.
Khairallah Naeem Ahmed, are you with us?
Yes.
Okay. Can you hear me? Our next presenter is Dr. Khairul Naeem Ahmed. His presentation about carbon monoxide desorption and reduction studies of a graphitic carbon nitride supported nickel catalysts. He's from University Kebang San, Malaysia. Dr. Khairul Naeem, you have like 10 minutes. Sorry, because we are run out of time. So please, the floor is yours. Thank you very much.
Okay, thank you. Assalamu alaikum and a very good afternoon to everyone. Okay, my name is Ibrahim and I'm from State Masan Marshall, Iran. Our work entitled Carbon Monoxide Desorption and Reduction Studies of Graphitic Carbon Nitride Supported Nickel Catalysts. Okay. Firstly, we will go through a bit introduction about the graphite carbonate. So firstly, the structure is inspired by the graphite, which is in layer structure, with each layer consists of carbon and nitrogen in the polymer form of estrizing and heptazine aromatic rings. And also it can synthesize by a simple procedure using the carbon and nitrogen containing compounds such as melamine and urea. So furthermore, there are some characteristics of the carbonate that makes it versatile catalyst support. First one is it possesses the hydrophilic ability and nitrogen-rich basic sites to improve the dispersion and of metal particles. Secondly, the surface area and the pore size, the pore structure are modifiable, and this can enhance the catalytic performance for the higher surface catalysts. Okay. So why we want to study the behavior of carbon monoxides towards the nickel-supported carbon monoxide catalyst? First of all, as we know, CO or carbon monoxide is highly reactive molecules, and it has been used as feedstocks in many chemical reactions, such as to produce fuel, such as methanol, methane, and so on. So apart from that, CO also is considered as a strong reducing agent aside from hydrogen and metal hydride. Therefore, it is interesting to study the behavior of carbon oxide molecules on either in reduction or resorption on the nitrogen on the nickel-supported catalyst surface. So, since we are studying carbon monoxide behavior in our catalyst, we will test the catalyst in the reaction that involves CO, which is CO detonation. So detonation is regarded as alternative to fossil-based natural gas, where the CO reacts with hydrogen to produce methane and water. And the most practical catalyst is nickel because of its high activity and low cost. However, due to the atomicity of the reaction, support material is vital to improve the thermal stability of catalysts. Okay. The experiments are described as follows. First one, we synthesize the catalyst, the nickel-supported carbonated catalyst using the impregnation method with 10% direct catalyst. And secondly, we conducted the resorption studies using the TPD or temperature program reduction, and the reduction by CO using the TPR, temperature program reduction. And next, we conducted the characterization by SRD, X-ray diffraction, nitrogen resorption, and X-ray photoelectron spectroscopy. And finally, we conducted the methanation performance test using the microreactor and mass spectrometer analyzer. Okay. Now we continue to the results and discussion. First, I will present the TPD analysis, which is the desorption of carbon monoxide. So as you can see in the graph, so pure nickel, if we use the clinical show no desorption peak of carbon monoxide. However, if we combine the nickel and carbon monoxide as a catalyst, there is three peaks of CO carbon monoxide peaks at 500 and until the 750, and it shows the interaction of nickel and carbon monoxide support leads to the enhanced carbon monoxide resorption and activation on the active sites. As we know, the carbon monoxide support contains two types of basic sites, which is the bronze state basic nitrogen and Lewis basic nitrogen. Okay. Next, we go through to the TPR studies, and we can observe between the nickel oxide and nickel supported carbon monoxide, there is a difference, as the nickel oxide shows two peaks, two reduction peaks, while a nickel supported carbon monoxide shows one peak. And the first peak at 420 to 440 is can be attributed to the combination of partial reduction and also the partial reduction of nickel oxide and the Bodak reaction. And for the nickel oxide profile, there is a peak at 460 that that we can attribute it to the complete reduction of nickel oxide. So as for nickel supported carbon monoxide, the catalyst should enhance reducibility because there is a complete reduction of nickel oxide at lower temperature than pure nickel sample. However, we detect a negative peak at 582 degrees, which is we can ascribe to the CO produced because CO is produced by the reverse product reaction. Okay. Now we conduct the characterization of catalyst to study the physical and chemical properties of the catalyst. The nickel supported carbon monoxide catalyst has been analyzed by SRD, and as you can see, the catalyst we label as B. And you can see it has the lower diffraction peaks of nickel oxide compared to the pure nickel oxide, which shows the good dispersion of nickel species on the support. Besides that, there is also low intensity of carbon monoxide peaks at 15 degree and 37 degree, which explain the presence of nickel species inhibits the crystal growth of carbon monoxide. Interestingly, we also can see the high crystalline of nickel diffraction peaks, which indicates the partial reduction of nickel oxide during calcination, where the carbon monoxide acts as reducing agent. Okay. Next, as for the nitrogen resorption analysis, we can see our catalyst, nickel supported carbon monoxide catalyst, shows the mesoporous characteristics, and also the reduced pore size due to the pore filling by nickel species on the support. Okay, and also the data of the BT surface area shows 7-fold increase, and the pore volume increased by 5-fold compared to the bulk carbon monoxide or support, which we can explain by the support has undergone the thermal exfoliation during the calcination process to form thin sheets and mesoporous structure. So now we proceed to the SPS analysis of the nickel supported carbon monoxide catalyst. We can see based on the spectra C1s and N1s, it shows the presence of the CN bonds in the catalyst, which confirms the characteristics of calorific structure of carbon monoxide. Furthermore, in the nickel 2P scan shows the presence of metallic phase, which confirms the occurrence of partial reduction of nickel oxide by carbon monoxide support during calcination, consistent with the SRD data. As for the CO methanation performance of the nickel supported carbon monoxide catalyst, we can see the high activity is achieved at 375 degrees C, in which 79.7% of CO conversion and 73.9% of methane selectivity are shown. This good performance can be attributed to the improved CO absorption and activation on the active sites, as well as enhanced basic sites on the catalyst surface. However, lower methane selectivity is due to the side products such as CO2 from water gas reaction. And this can be explained by the strong interaction between CO and active metals based on our TPD result. Okay, as the conclusion, the addition of the graphitic carbon monoxide support to nickel-based catalyst improved the complete reduction by carbon monoxide at lower temperature than pure nickel oxide. And secondly, nickel supported graphitic carbon monoxide catalyst demonstrated the strong resorption of carbon monoxide on the active site of the catalyst, which can be attributed to the increase of basic sites. And lastly, the good CO methanation performance of nickel carbon monoxide catalyst can be ascribed to the enhance of CO absorption and activation on the active sites, as well as the surface specificity. With that, thank you.
Thank you, Dr. Khairul Naeem. Thank you very much. Any question? Okay, I think this is the last presentation, so everybody I think is hungry. So thank you again, Dr. Khairul Naeem, and maybe next time, inshallah, we see you here in Jordan. Thank you guys for your patience, and I believe we are all hungry, maybe starving, so it's time for lunch. Thank you guys.